Great. So this is our conference week, by far the most populated. So this means we have to be extra careful. Maybe also the most fun with all the people that are here. I want to thank the other organizers, but especially Lin J for helping make this happen. The local organizer really is the one doing all the work, I'm afraid. So we owe her a lot of thanks. And then also the folks here at GGI, the staff who are helping make this happen. So with that, I'm going to hand it over to our session chair.
Am I allowed to take off my mask?
You're allowed.
Yeah, I think the speaker doesn't have to wear it. Yeah. But seriously, for the rest of you, I mean, I heard from other participants, it's really not fun flying to Florence and spending the whole time quarantining in your hotel room. Okay, so it's a pleasure to have Juan Maldacena from Institute for Advanced Study, who's going to tell us about black holes. I don't know whether for people with lots of time or for people with not so much time. And then he's going to do the first half. Lin is going to do the second half.
Okay, so this talk will be split in two. So I'll give the first half and Henry will give the second half. And it will be based on a paper that we wrote with Henry and Lisa Rosenberg and Jerry Shen. So let me start with some motivation. So we are interested in quantum gravity. And then two-dimensional gravity, in particular JT gravity, is a nice system because quantum gravity in that case becomes particularly simple. There is just one boundary mode that can be strongly coupled. So the quantum gravity effects can be non-trivial, but yet they can be solvable. And so analyzing this theory is a window into strongly coupled quantum gravity. Actually, to be more precise, that theory contains two parameters in some sense. So it contains, in addition, so-called bulk entropy, which governs the strength of the non-trivial topologies. And we are going to, in this talk, throughout this talk, we'll ignore the contribution from non-trivial topologies. So we're going to ignore effects that go like e to the minus S naught. So S naught is the parameter governing higher topologies, and so higher topologies contribute with this number, and so we're not going to include these effects, but we're going to include effects that go like 1 over S naught to any power. Okay. So in this limit, the theory reduces to, let's say, the Euclidean theory, reduces to a theory on a disk topology, but with a boundary mode that is dynamical and can have strong quantum fluctuations. And the goal is to understand some of the effects of these strongly coupled quantum fluctuations. Now, this problem has been analyzed before by Shenbin Yang and Kitaev and Su, and they understood how to quantize this boundary mode in the case with node supersymmetry. And so in this setup, when we go to very low temperatures or very long times, these boundary fluctuations become strongly coupled, and that's the regime we would like to understand. I think we'd like to understand how to think about gravity in this particular regime. In some sense, we have the solutions, and I think it's an interesting regime that we haven't fully understood, and I'll try to explain what is surprising about this regime and what we'd like to understand. Now, there are a few lessons that we've already learned about this regime, and the first lesson has to do with computing the partition function of the gravity theory. At the simplest approximation, let's say the classical approximation, the partition function is just simply a constant given by the entropy, the exponential of the entropy. Okay? This is the naive classical formula, and the quantum corrections that these authors I just mentioned understood give a correction to this formula, and also this was computed by Stanford and Witten, and it's a correction that becomes important at low temperatures. So at very low temperatures, we have an extra factor here of beta to the 3/2, and which suppresses the partition function at very low temperatures. So it is as if at very low temperatures we get less and less states. Okay? In fact, we can translate these results, and well, also some results at higher energies, into, well, let's say this result into a density of states which at low energies behaves like, well, the e to the s naught times square root of e. Okay? So we have a density of states which, as a function of e, has a big factor e to the s naught that gives the classical entropy, but then it becomes 0 at very low energies, okay? At least in this approximation. In this approximation, we don't see any sign of discreteness of the levels and so on. For that, we will need to go to higher genus. Very good. So now, so that was the case with no supersymmetry, so n equal to 0. The computation was also done in the case with n equal to 2 supersymmetry, and also n equal to 1. N equal to 2 is more interesting, because in that case, what one finds in this same approximation is, first of all, that the partition function at very low energies indeed goes like this. So there is no correction to this behavior at very low temperatures. And the corresponding density of states has a little gap here, so some energy gap, E gap, times, and then there is a delta function at 0. So there are a bunch of states with exactly 0 energy that preserve supersymmetry. And then there are a bunch of states that that form a continuum with some energy above this energy gap. Okay. Now, the scale of this energy gap is set by the coupling in front of the Schwarzian theory. So the modes that govern these fluctuations are governed by a Schwarzian action, which maybe I should call it I, so not to get confused with the entropy. So there is some coefficient here in front. So we have a function which, so this is the time on the boundary theory, and this f can be viewed as a time in, let's say, Poincare coordinates or some time in ADS, and this whole thing, this is a Schwarzian derivative, which I presume you're familiar with its expression. What's important is that it contains a net number of two derivatives, so that means that this quantity is a quantity with dimensions of length. Okay, so there is some dimensions of length quantity, some overall constant in front, and this EG is of the order of 1 over that length. Okay. Now, this theory contains no dimensionless coupling. Contains just this length scale, which is phi r. So that sets the length scale at which the theory becomes strongly coupled. Okay. So you go to distances of order this length scale, then the theory becomes strongly coupled. Now, just to orient yourself for the meaning of this length scale, let me just mention that JT gravity can arise from the low energy limit of near extremal black holes. And so if you have a near extremal black hole, so there is the R 1,3 here, so the 4-dimensional Minkowski space far away. There is, let's say, a 4-dimensional black hole which size some extremal radius RE, which sets the radius of the sphere and so on, the size of the black hole. And then here we have some ADS2 region, or nearly ADS2 region. And in this context, this length scale phi r we are talking about is just the size of the black hole times the extremal entropy of this 4-dimensional black hole. So this is just translating to more familiar language of 4D black holes. Okay? So in other words, for 4D black holes, there is at very low energies this mode that we can think as a boundary mode in ADS2. Of course, this mode is somehow localized in this region that joins the ADS2 with the 4-dimensional flat space. That's where it is in the full geometry. Okay? Very good. Okay, so now we'll try to consider this theory. And we're going to consider this theory mainly because at low temperatures and low, let's say, in Euclidean time, so as to project onto these ground states and see what we get in that regime. Okay? I think so. We think that conceptually the problem is similar whenever we take the low energy limit, but the low energy limit is cleaner in this supersymmetric case because there is this gap, and then you are sure you are really talking about the ground states. In this case, it's a little slightly more subtle, but maybe Henry will discuss a little bit about that case too. Okay, so let's focus on this theory at very low temperatures. Now, this boundary action, in this case with supersymmetry, is the same as this, plus there are some fermionic and bosonic partners. So it's basically conceptually the same thing as we had before. And so we have these fluctuations, and the details of why we have a gap and so on have to do with the details of this boundary mode. So it's not that you see it clearly in the gravity theory. I mean, well, you see it clearly mathematically, but...
Hey, Juan?
And perhaps one of the interesting... Yeah.
Sorry, can you just clarify like how much supersymmetry is n equals 2? Like, is that maximal supersymmetry, or is that like 40?
No. Well, n equal to 2 is yeah. So n equal to 1 is just one supercharge. So there is the Hamiltonian and one supercharge. N equal to 2 is the Hamiltonian and two supercharges. The theory will also have an R symmetry that rotates these two supercharges. And n equal to 4 is the amount of supersymmetry that the black hole in flat space has. So if you want a black hole that has n equal to 2, you would have to go to a black hole in ADS. So that's a higher dimensional case where you have this amount of supersymmetry.
So you don't necessarily expect things like holomorphy to be useful or whatever for n equal to 2?
It's useful for some things, but we didn't find a terribly good use for it. Maybe someone can find a good use. Yeah, so we didn't do n equal to 1 because n equal to 1 doesn't have this behavior. But so this is the first time that we get this behavior. We also get the same behavior for n equal to 2 as Turiachi and Heidemann. Sorry, all the references are in our paper, so I'm not. So people have considered this before, and they've understood this in a paper by, I think, Iliesu, Turiachi, Heidemann, and I'm forgetting one author. If he's here. You're here? No. Okay. I thought someone lifted. Okay, very good. So now, what is funny about this limit is the following: that when you project onto these states, it looks like now we have a Hamiltonian which is exactly 0. So in some sense, somehow there is no time, right? There is nothing is going on. Things are frozen. Okay. On the other hand, when we go to low energies in this picture, we have some person here who is at the very bottom of this throat, but this person continues to have his or her own time. Okay. It's perfectly happy here. This person says, I'm not frozen, I'm perfectly happy. Okay? So everything, the freezing has to do with the translation to the boundary observables. And so it's a curious thing that I have to say I don't fully understand, but so I'll tell you various computations, and I think the goal of this was to understand this a little better. And I think it's an important, I think it's interesting to have a system which you are sure has no time, but nevertheless the bulk has some time. So it really forces you to think about the emergence of time, the emergence of bulk time, and how to do that, and so on. And I think what we'll discuss today is mostly scratching the surface on this. We don't have like a very nice picture of how the bulk time emerges. We'll make some remarks, but yeah, please.
You're saying that the boundary theory has no time because the energy is exactly 0? And
Yes.
I mean, for a non-gravitational theory, I can always shift the energy to any other value.
Yes. Well, so what I mean is that all the states relevant have the same energy. In fact, I mean, I should emphasize that part of what we are saying here is not too peculiar to this n equal to 2. It's cleaner in this n equal to 2 situation. But it's present even in this other situation if you restrict to very narrow band of energies and so on. So it's also present in other situations. But it's, I think, cleaner in this case because you really have lots of states here. You don't have to worry about having some corrections. Here you could say, well, if you restrict enough, at some point you're left without states. Or there could be potential room to hide here. There is no room to hide here. You have to face the problem more clearly.
And maybe this is what the rest of the talk is about, but if you're really truly in the ground state, how can you have an observer in the ADS2 throat? I mean, wouldn't that contribute some energy?
Yeah, I think the answer to that will be more clear. Yeah, will be more clear later. Yeah. So. But please ask questions. So in this regime, but maybe I'll get here. So in this regime, we could calculate all kinds of correlators. So I mean, people in the past have, of course, calculated the entropy in this regime, and there are lots of papers calculating the entropy, wonderful papers, and lots of very detailed agreement. So here we're trying to focus more on trying to understand correlators, and in principle, usually a technique that we normally use in ADS-CFT to understand what the bulk observer is doing is to look at correlators. So we can look at correlators in this regime, and then take the very large, so the boundary times, we take them to be extremely large, and in that regime, the calculation becomes independent of time, okay? So we'll have that the correlators, so which are calculated by, well, Henry will discuss it in more detail, but they are basically a Witten diagram dressed by these boundary propagators, and in this regime, they become completely independent of the boundary time, and they have an interpretation in terms of the trace of some operators. So this will be some operators which are projected to the infrared, okay? So operators which have undergone an infinite amount of Euclidean evolution, okay? So projected onto the, so this is the boundary interpretation. This is some calculation in the bulk, and then there is an e to the S0 business. Will you mention the type 2 discussion? Type 2 algebras? Yeah. Okay, very good. So that's what we would get here. And so, well, now I'll discuss just the simplest correlator, which is the two-point function. Okay. So for a two-point function, the discussion is relatively simple. So we have, we can think of the two-point function as some correlator that we calculate on the two-sided system. And so a two-sided system has a gauge invariant variable, which is the length of the wormhole, so we can call L. And this length has an action which is L dot square, so it has a Liouville-like action of this form. So that's the action, and we can now quantize the action and get the answers. And in the non-supersymmetric case, so we have simply, this is all we have, and so we have waves that come in and out, and those are all the continuum states. So various energies, you can do this, you can calculate the wave functions and so on, as many of you here have done, okay? So what's the difference in the supersymmetric case? Well, the difference is we have some extra super partners, and in particular, because we have two supersymmetries on the left and some supersymmetries on the right, so anyway, so we have some supersymmetries, and there will be some fermions which are the partners of the left supersymmetries, and so on for the various ones. So we have like 4 fermions, and the action will contain the L dot term. There is also a Wilson line term that has to do with the U1 gauge field that we have in the bulk, dual to the U1R symmetry, that you need for the details, but not for the point I'm about to make. And then we have some terms involving fermions here. Some Yukawa-like terms with various combinations of the possible, all 4 fermions that appear here. I'm not going to write them in full detail. But the basic point is that depending on the quantum, so these fermions, well, you can combine them into a pair of qubit degrees of freedom and so on. And depending on the states of those qubit degrees of freedom, this could be positive or negative. That's the essential point. And because this can be positive or negative, then this means that this potential now contains a piece, well, I'm now talking about this action as a function of L. So there will be the leading term for large L is this one that will be negative, so it goes down. And then there is this positive piece as before, and so it goes up, okay? So again, we can send waves from the left and the right, and there's continuum states, but the new thing is that there could be bound states, okay? And when you analyze it in detail, you find that there is actually only one bound state. One bound state, and it has 0 energy. So there is just a E equal to 0 bound state. And with the simplest quantization of the R charge, that bound state also has R charge equal to 0. Okay? And it has a wave function, which, if we were to draw it here on the same plot, is a normalizable wave function. So this is I'm here now plotting psi of L. Okay. So that's the normalizable wave function, which says that this wormhole has some fixed length. So if you go to the ground state, the wormhole is not becoming very long, but has somehow fixed length. In the case, in the usual case, when you go to low temperatures, we have less energy to climb this potential barrier, so the wormhole becomes bigger and bigger as you go to lower and lower temperatures. In this case, as you go to lower and lower temperatures, the wormhole has some fixed size, okay? Some size which is fixed. Now you can say, well, what is that size in some units that I care about? So in this, so that distance of the wormhole goes like, in the case of the 4-dimensional black hole, it will go like the logarithm of the entropy, of the extremal entropy, okay? So it's set, I mean, some distance that's set by this phi r and so on, and once you translate it this way, if you had a pair of 4-dimensional entangled black holes in the thermofield double state, and you go to this very small energy limit, the wormhole size does not go to infinity, the length does not go to infinity, but it stops at this value, okay?
Sorry, Juan?
Yeah.
Where is the S naught in that action I that you wrote down?
Well, I was careful to distinguish SE from S naught.
Oh.
And the reason I said that is because in the 4-dimensional case, the extreme, so there is phi r is given by RE times SE, right? So in JT gravity, we have two independent parameters, which are S naught and phi r.
So SE doesn't include the S naught part, or it does?
Well, this is for the black holes. This is JT gravity.
Yeah.
So let me write the two parameters of JT gravity in terms of the parameters of 4D gravity. In 4D gravity, we have SE, which is the same as S naught, JT gravity approximation. And we also have phi r, which is basically the radius of the black hole. This is a dimension-full parameter. So when we say this is phi r, we are saying that we are measuring time in units of the flat space. Really, I mean, in some sense, this is not really a parameter of the JT gravity theory because it's dimensionless. It's dimension-full, sorry. There's no dimensionless parameter associated to this. But if we have a preferred choice of time, as we have in this, then this is.
So you say it comes from, because you express things in terms of R, E, and S, something like that?
Yeah, because, you can, so we have two parameters here, and there are two parameters.
Because I thought that action just depends on phi r. I'm not.
That action depends purely on phi r.
Okay, I see. So, all right.
Yes. So if you think about it this way, then what happens is that D is the same as what we call L here, plus there is a log of let's say phi r over epsilon. Okay, and this is something that appears when you take the JT gravity limit, and that's the distance to the boundary. So I just. This is all identical. There is nothing important here. This is just translating parameters. Yeah.
This wave function is time independent?
Time independent, yes.
So why isn't this a paradox? It looks like you can communicate between the two boundaries.
Yes. So the question is, well, but also the fact that it's time independent means that you are not moving along this boundary, right? So this idea that we're moving along the boundary is some idea that comes from having a superposition of various different states. So the state is time independent, and so for all times, let's say you just have this Wheeler-DeWitt patch, and that's what you have for all times. It's not that at some later time you'll have this Wheeler-DeWitt patch, okay? So we have a time independent state, and yeah. Yeah, so having a better, I think we don't have a very good Lorentzian picture for the space-time, so all we can say is something like this, and I think it would be nicer to understand that better. Okay, I'm almost out of time. So now finite length. So then now this fact implies that if we calculate the correlator, the 2-point function, then the 2-point function is given by correlator of the form. So we take that ground state, let me call it 0, calculate e to the minus delta L, that's the trajectory of a particle going from here to there, and then 0 again. Since the state is normalizable, we'll just get a finite answer at long distances. Okay. Now you can do the correlator also for all possible times. So I was talking now about the very long times, which is a constant, and then here it behaves as 1 over u to the 2 delta. Okay. So that's the 2-point function for all times, and at long times it goes to this constant that we can calculate this way. Okay. Now, so this constant value has some interesting, so there is, if we go back to the, some number which depends on delta, but nothing else, and once you put in the factors of phi r and so on, in units, in some more natural units, this goes like SE to the 2 delta. So that comes from translating phi r to some. So if you normalize the 2-point function to be of order 1 here in the outside the black hole, then that same operator projected onto these ground states and so on will have a very small 2-point function of this form, power suppressed in the entropy. And that power suppression is just simply saying that the field has to propagate all the way to this distance that we were talking about before. Okay. And so we can interpret also this 2-point function as the typical eigenvalue of the operator. So there is also, this is unnormalized, there is an e to the 2s0. So this is the typical value also of the eigenvalues of the operator. So you can think that you could imagine picking a set of states that has definite eigenvalue for this operator. And then those operators should have some structure at this distance, which is of order log of SE down the black hole throat, you would say. This would be the most naive interpretation. Okay, I'm about to finish. So now, so if you think about fastballs and so on, you could imagine fastballs might be some basis that diagonalizes some simple operators. And then, of course, the 2-point functions will give you the size of the typical eigenvalue. Well, the typical eigenvalue would be the typical structure that the states have to differ at this level. They should not differ further down, because if they were to differ only further down, then there will be a further suppression factor. Okay. Okay. Now we've also well, it was really done by Henry. So the SYK. So Henry did a simulation for SYK. For the n equal to 2 version of SYK, and then this you can check these numbers. So you can calculate also these numbers, and you check that, well, these formulas work in the sense that these constant values of these constant values are in agreement with between this theory and the numerical calculation. Okay, within a few percent. So that was done for n equal to 16. Okay, okay, very good. So, and that was done for a few operators. So you can do this for the fundamental fermion operator, for products of fermions which carry R charge, and also for operators that do not carry R charge, like this one. Okay, so and you can say this is like a test of quantum supergravity, right? So you computed this using gravity. Of course, this was done also before for ordinary JT gravity, and we are testing the quantum dynamics of gravity using this SYK model. Okay, thank you. Now Henry will continue.
Testing? Does it work? Cool. Okay, so Juan discussed mostly the empty wormhole. And now one way to motivate what I'm going to talk about next is discussing wormholes which still are at 0 energy but have some matter on the inside. So in particular, so Juan calculated this formula, which tells you the length of the wormhole when there's no matter on the inside. And we also said that the entropy is just SE, right? The question now is what happens when we add matter? So what happens to both the length and what happens to both the entropy? Okay. But actually there's a zeroth order question which Raphael asked, I guess, which is there even a wormhole when you have matter on the inside? Of course there's a wormhole at finite temperature, but the question is whether you can really bring it down to zero energy. Okay. In order to answer this question, well, there are two methods. One is you could just do the SYK calculation, insert some matter and calculate the correlation functions, and you see that they're non-zero. So that's evidence that if you insert some matter, you can really, the zero energy states still survive. But of course, we'd like to understand this theoretically as well. And the way to do that is to calculate endpoint functions. So in particular, we would like to calculate something like this. So here we've inserted a particle. So if we cut this state open, right, this is the thermofield double. We've now inserted some matter inside the thermofield double. And we'd like to do something like measure the length between the two sides. Okay? So this is some 4-point function, which happens to be, it's the so-called out-of-time order correlator. Now, this Liouville theory that Juan discussed knows a lot about the bulk, but it doesn't know everything. In particular, it only knows about diagrams, roughly speaking like this, okay? Involving lengths in various orders. These are basically, if you look at the state on each of these slices, it's the empty wormhole. So this Liouville theory actually doesn't know about what to say when there's matter on the inside. So we need a slightly more souped up formalism. And if you're familiar with the JT gravity discussion, even for the n equals 0 case, you'll have a guess for what I'm about to say, which is we need to calculate the propagator, the so-called propagator formalism. So to explain that, well, let me just briefly review the case first. So the problem is you have ADS, and let's say conditioned on the fact that you start at some location in ADS, you want to know where the boundary particle is going to be in the future, okay? So the goal is to calculate some function which is a function of 2 points, 1 and 2, right? Okay. In the case of ADS2, right, that's just 2 bosonic variables here and 2 bosonic variables here. Okay. When we go to the supersymmetric case, of course, we're going to have Graspin variables, sorts of stuff like this. But conceptually, this is the goal. It's also a function of u, the proper time along the boundary, right? In our case, we're going to take u to infinity, right? Because we're interested in the ground state propagator. So that's the case, right, where you take the Euclidean time to infinity. Okay, well, how do you calculate this thing? Well, this is roughly speaking, right, just the sandwiching, you start at some point 2, you evolve with the Hamiltonian, and you get to point 1. And the details is, of course, what this means. So in the case of n equals 0, right, you can represent the ADS2 as some quotient, SL2 mod U1, right? So if you're not familiar with this, you can think of the sphere, right? The sphere is a quotient of SU2 mod U1, right? And when you take, for example, if you think of a particle on the sphere, right, you can think of that as a special case of the general discussion of a rigid rotor, right? So a rigid rotor is described by SU2, and then when you consider the limit in which a rigid rotor becomes very long and narrow so that it becomes a point that just sits on the sphere, you're taking one of the moment of inertias to be very tiny, and then you should quotient by the U1 that's related to that moment of inertia, right? Right. So if you have a Hamiltonian of a rigid rotor, it's roughly like this, right? There's some jz squared times something here, and if this is very tiny, there's a huge penalty for any jz rotation, so you should simply set jz equal to 0 in the low energy theory. Okay, so that was the case for the sphere, and the case for ADS proceeds by analogy. So now you consider functions on the group manifold SL2, and you quotient by some subgroup U1, and that gives you particles on the hyperbolic plane. One subtlety is that you want to actually impose that the particle has some charge under this U1. It's not charged 0 like the case that I just described, but it has some spin. And this is related to the fact that the Schwarzian is not a free particle, but behaves like a particle with a magnetic field. Okay, so that was n equals 0. Now for n equals 2, the natural idea would be to take the supergroup version of SL2, which is something called OSP22, and then quotient by something. Okay? Actually, we spent a lot of time talking about what the something is, but I will spare you of the details. What is OSP22? It's just the superconformal version of the SL2, right? So SL2 is just satisfies this algebra, right? Something like this, right? And there's some superconformal version of this. If you want to know the details, it's in chapter 19 of Polchinski. And so for some people like me, people in my generation might be shocked to hear that there are actually 19 chapters in Polchinski. But I assure you that it's in there. The only interesting thing that about this group is, for example, that we have some fermionic generators. So we have 4 bosonic and 4 fermionic generators. And some of the generators, the fermionic generators, they commute to the bosonic generators, right? Okay, so in particular, this formula, so in the previous case, we had to mod out by U1, and in this OSP2 case, we not just mod out by a U1 that corresponds to a bosonic generator, but since there's some fermionic generators that commute with that bosonic generator, we also have to treat them in some way. So that's all in the something. Okay, so at the end of the day, once, it doesn't sound like I've said very much. It sounds like I've just told you about some group theory stuff. But if you know how to treat the gauge symmetries properly, that's enough to fix the supercharge of this theory completely. And so we're able to write down what the supercharge is. And then we simply impose some equation that says that Q of the supercharge acting on the propagator annihilates it. So we have Q acting Q1 of this, Q2 of this, and then also the bars. And that's enough to fix the propagator completely. Okay, so that was obviously a bit of a sketch, but the final answer is P infinity 1, 2 equals something, which I'm not also going to write explicitly. But in particular, one piece of it that's a little bit interesting is that it involves this wave function. Well, okay. There are a bunch of fermions that I'm not going to write. But the dependence between 1 and 2 involves the wave function that Juan discussed, the bound state wave function. Okay, so the propagator between 1 and 2 has some complicated dependence, but it still, for example, prefers not to be too far away. Right? The second point doesn't want to be very far away from the first point because of the fact that there's this bound state wave function here. Okay, so using this explicit expression for P, you can compute the OTOC. By compute, I mean you can reduce the infinite dimensional integral over the Schwarzian mode, right, to just a finite dimensional integral. It's a finite dimensional integral over the various positions, right? So we have some diagram like this involving, let's say, 4 points here. We put some cross correlator, and we're left over with some finite dimensional integral that just involves the positions of these guys. It does not involve this wiggly curve that we have to integrate over. So that's a somewhat explicit expression. And using it, we can, for example, compute the heavy, light correlator, the heavy correlator, etc. There's some saddle point approximation. The only thing that I want to point out is that using this, for example, we can extract, so these are now 2 light operators and 2 heavy operators. We can extract from this the length of the wormhole when there's a very heavy particle sitting in the center of it. Okay? And the answer that we get in that case, let me write it one more time here. So, sorry, this was the length, the distance. There's the same constant, but then there's also a correction at very large dimensions that goes like log delta, maybe a 2, something like this. Okay, so what we found is that the wormhole gets very long, right, when you insert the particle that's very heavy. Okay, we also calculated the entropy. The entropy, I'll tell you first the result, and then I'll explain how you get there. So what we found is that the entropy gets shifted. It gets shifted by some value that I believe is, well, I can write down the numerical value. It's some order 1 value. And the only, there's a small purpose for me writing the value. Let's see. Okay, it's just 1/2 in this case. This is for a delta very big. So the extremal entropy gets shifted by a small amount. It decreases, and the length increases. So that's kind of nice, because what it's saying is that the correlations between the two sides, as measured by the distance, right? So simple operators are sensitive to the distance between the two sides. Those correlations are getting weaker, right? But the entropy is only shifting by a small amount. So that's qualitatively in the right direction, but what's a little strange is that it's telling us that somehow very complicated observables are still correlated, but the simple observables are not correlated in this limit.
Sorry, Henry, just to clarify, so if I understand correctly, you don't actually have dynamical matter fields. You're just treating e to the minus ml as kind of the Wilson line or something.
That's right, that's right. This is a probe calculation.
Yeah, thanks.
Yeah. That's right. So
Tom has a question.
And heavy means, so heavy is a geodesic, heavy is a geodesic that back reacts and light is a geodesic
exactly,
that not back reacts.
exactly.
And so the delta there, that's the heavy.
Yeah, that's this thing here.
And then you're thinking of the D
as the light thing. Yeah, exactly. Exactly. Okay, so that's what you get for delta greater than 1. I also tell you what you get for delta less than 1. So everything is light in that case. In that case, the distance doesn't change very much. And however, the entropy actually still shifts. And the entropy shifts by an amount, which is now minus 0.7 to something like this. The only point of writing this number is to show you that it's bigger than this number. So it's a little bit strange. So a light operator doesn't change the length very much. So it doesn't change simple correlations, but it actually shifts the entanglement entropy between the two sides of the wormhole in such a way that it actually shifts it a little bit more than for a heavy particle, which is a little strange. Okay, so now let me explain how you compute these entropies. Okay, so yeah, this is a nice computation because it doesn't involve any Grassmann integrals. You just need to know 2 facts. So in this case, for delta less than 1, we're considering a wormhole like this, right? Well, we're considering a density matrix. It's the density matrix of one side of the wormhole when you trace out the other, given that there's some particle in the middle, right? So you start with a density matrix like this, right? When you trace out the right side, you join these 2 edges, right? And you can redraw that as just something like this, right? So this is the one-sided density matrix. And when you compute, therefore, trace of rho to the nth power. So we're going to compute the entropy by taking trace of rho to the nth power, and then taking n goes to 1. What you get is some formula which, well, this is roughly 2n minus 1 double factorial in the case where the particles are light. And that's just coming from all the Wick contractions. So when the particles are light, the back reaction is unimportant, and you just get some combinatorial factor coming from the Wick contractions. And continuing this to n goes to 1 gives you this funny number. For the case where they're heavy, there's actually a similar trick. You don't count all Wick contractions, but because of this fact that I just mentioned, that the geodesic length gets very, very long when you have a heavy particle, that's telling you that all cross diagrams are suppressed. So you actually only need to sum planar diagrams. And when you sum all the planar diagrams, there's some different combinatorics, and that gives you this factor of minus 1/2. Okay? A slightly different way of saying it is for an operator which is projected into the zero energy sector, you get a semicircle distribution, right? So the cross diagrams are completely suppressed, so you only have planar Wick contractions. And the planar Wick contractions come from random matrix behavior, where the random matrix is perfectly Gaussian. Okay? So this tells us some sort of facts about the wormhole with matter, okay? But so far, well, we don't have a very clear explanation now of what exactly is going on, right? We did some computations, like involving the distances, involving the entropies, but we don't have a very clear and sharp description of, for example, the Lorentzian picture of these wormholes. Well, certain things we know, but for example, one question you could ask is, how is it even possible that we could have matter in the middle, given that the energy on the boundary is 0, right? Now, one version of the answer is that the bulk energy is not the same as the boundary energy, right? So in particular, for the Schwarzschild particle, right, in a two-sided situation, the left boundary particle carries some charge q left, the right boundary particle carries some charge q right, and some matter can carry some charges here, q matter. And what we know is that the left boundary has 0 energy. That tells us that the left Casimir is 0. The right Casimir is also 0 because it's a BPS wormhole, but q matter is non-zero. So we're claiming that such a configuration is possible. And you might find this equation, this was equal to 0 by the gauge constraint. Okay? So you might find this equation quite surprising, but it can be satisfied since q is not a vector in Euclidean space, but a vector in Lorentzian space, right? So if you have two null vectors, ql squared is 0, q right squared is 0, but q matter squared does not have to be 0. Q matter squared could be very large. I don't know, whatever you want it to be. Okay? So what we're saying is that there's no boundary energy, which is like q left squared is 0, q right squared is 0, but there can still be bulk energy, q matter squared. And the existence of bulk energy is, of course, related to bulk time. So somehow the conjugate of energy, right, is time. So there's a bulk time that can be somehow experienced, but the boundary times are still 0, right? Now you could wonder, what operator, qm squared, is this really? Like, I've constructed it in gravity. Well, I haven't even told you how to construct it in gravity, but it can be constructed in gravity. It involves the length mode between the two sides and various derivatives of such things. But what is it in the boundary? And we don't have a very satisfactory answer for that. But it's some way of distinguishing the various states of the wormhole, right? So not all states are perfectly the same. In particular, right, the state with no matter at all was the maximum entropy state. And now the states with matter have a different value of q matter squared, but they also have, for example, different entropy, they have different lengths, and so forth between the two sides. Also to make the comment about the type 2 algebra, the fact that there's a maximum entropy state, which is the empty wormhole, is kind of similar to de Sitter, right? So there's, again, some maximum entropy state, and then any excitations of that state will bring down the entropy between the two sides. So that's similar to de Sitter, and that's called type 2-1 apparently. Let's see, what time is it?
You still have 10 minutes.
Oh, cool.
Oh, we should? Okay, let's 5 minutes.
Okay. I'm also happy to Okay, let me make some comments now on the n equals 0 case. So far we've been mostly discussing this gap and so forth, and we've been discussing properties at 0 energy of the n equals 2 model, but we can also discuss what happens at fixed energy in the n equals 0 model, right? Fixed, but let's say low energies, just so that the quantum fluctuations are large. Okay, well, imagine computing, well, let's just try to redo what Juan did, but in n equals 0, right? So you're supposed to compute the length between the two sides, for example, right? So this is some correlator, let's say. This is given by e to the delta L dl, psi of L of e squared, right? And then some times, e to the ue, right? Now, the only point of, there's also an integral over energies and some density of states, rho e, right? So in the n equals 0 case, right, rho e has a square root of edge dependence. That's what Juan mentioned in the beginning. And plugging into this formula and taking u very large, we can make the approximation that we just simply put, well, let me call this e and this L. We simply set e equal to 0, and then we look at this formula, okay? If you look at this formula, you will see that the only part, right, that contributes some time dependence is this piece here, right? So since then by dimensional analysis, the answer is just 1 over u to the 3/2, right? So you have some e to the 1/2, e, and since u is inverse of e, you get 1 over u to the 3/2, right? So this is telling us that at long times, these 2-point functions are decaying now, right? And they're decaying in a universal way. Like the dependence, for example, on the dimension of the operator is totally gone in the power law, right? So originally there was some power law dependence, which of course depended on the conformal dimension, but now that's washed away, and there's just some number here which maybe depends on delta, okay? Similarly, if you look at some higher point functions, There's some blob here. You can argue that you simply just get a product of the different U's. So there's U1, U2, U3. You simply get a product of the different U's, and you get something here which depends now on maybe the couplings of the theory, the masses, and so forth. But the overall time dependence is completely universal. So in that way, it's very similar to the n equals 2 model, where we just had constants. So we didn't get this piece, but we still had a bunch of constants. These constants somehow tell us about the theory, but there's some time dependence which was in some sense trivial. The exception to what I'm saying is if you have some sort of connected correlator. So if you have some connected correlator like this, you do not get a product of times. And one simple way of seeing why that's not true is if you have some times U1 and U2, the answer in JT gravity, this is just some wormhole, right, with no matter cutting it along the slice. So the answer must only depend on U1 plus U2. That's because the energies are the same on both sides of the thermal field double, right? Since H left equals minus H right, H left equals minus H right, H left equals H right on the thermal field double, U1 and U2, the time dependence can only come from the sum. And this means that there's some revised formula where if you have a disconnected contribution, you get things like U1 plus U2. So you lose an overall factor of U to the 3/2 when you have connected versus disconnected, okay? So this in particular means that connected diagrams are all enhanced over the disconnected diagrams are enhanced over the connected diagrams. And in particular, this means that, for example, this entropy computation that I was just discussing has some there's a lot of similarity in this low energy limit, for example, right? Because in this case, we also saw that there was a suppression of the connected component versus the disconnected component. Okay, so, well, there's more to say, but the overall message is that, as one said, the n equals 2 case is a bit cleaner. We have a nice bound stage with some finite lengths and so forth, and there's a gap that separates all the other stuff that you can hide behind. In the n equals 0 case, however, conceptually, it's quite similar. If you simply fix the energy, there's also no non-trivial time dependence, right, on the boundary. The time dependence is, just given by some oscillating, e to the I et, right, energy eigenstate. But there can still be some sort of interesting bulk time dynamics. And that's also due to, we think, to the fact that the matter Casimir is not obviously related to the boundary Hamiltonian. Okay, so I'll stop there.
So questions for Henry?
Or Juan.
Or Juan? Tom? Did you hand him the mic?
So I'm trying to understand the picture of the Lorentzian. I know you said maybe you don't understand it, but so if we just start with a black hole in ADS2, if we put a particle in the middle, then it's like a long, wormhole with a lumpy middle.
Talking to your mic.
Sorry, it's like a long wormhole with a lumpy middle. I guess from that picture, it looks like maybe there's a phase transition between two different extremal surfaces, and there's some Ruta-Kanagi formula type calculation of the entropy. How is that related to these calculations?
I think you're having in mind a situation where the matter is mixed, right? And then there can be a transition. Is that what you have in mind?
No, I'm just talking about the two sides, depending where we put the particle.
I see. Yes. There's two RT surfaces, one here and maybe one here, something like this, right?
Yeah.
Yes. Well, here there's no QES formula that we know of, at least.
Because you have to sum diagrams, is that why?
Well, we're not using any, well, okay. First of all, when I did this computation, I didn't assume any replica symmetry breaking, right? I had all sorts of diagrams which, had no obvious symmetry, let's say, some diagram like this. This is a replica, I don't know how many n's I drew, but let's say it's n equals 4 or something. There's no n equals 4 Z4 symmetry. But you can ask, for example, well, I'm not sure if this is what you're asking, but you can ask, for example, whether you can detect, if you measure the relative entropy of one side of the thermofield double, right, can you detect what the state of the matter is inside the middle? That's related to the question. Yeah, and it's a bit weird. Yeah. What the answer is, for example, if you try to distinguish a state of the wormhole with matter and without matter by just doing one-sided experiments, you can do it, but the relative entropy is not going to be extremely large, right? It's going to be of order 1. So that tells you that you can learn something about the state of the particle maybe in the inside, but it's not like in the standard situation where one side knows everything and the other side knows nothing. Here it's like both sides know a little bit about the state of the matter in the middle.
Okay.
Yeah. So in other words to say it is that there's no, the RT formula is some classical formula, right, which is true at high energies, and the boundary mode is rigid in that limit. I don't know of any way to use an argument like the RT formula in this highly quantum regime. Yeah. In particular, maybe you could say that these fluctuations are a bit like matter, you could say that this boundary graviton mode is a bit like having entangled matter, where the matter is a graviton, but I don't know how to make that precise in any sense. I don't know. Yeah.
Anyone else?
Yeah, maybe I should have emphasized that, this is some computation in the bulk where there's no QS prescription, no replica symmetry, but we can still do it. And we can do it just because we know how to sum diagrams. We know how to compute endpoint functions. We know how to compute endpoint functions because we did it using this propagator formalism. That's the,
Juan?
I have a comment on that question. So, I mean, in principle, the bulk would have propagating fields. It's not something in the probe approximation. So,
In principle, yes, I agree.
yes.
Yeah, but the method of calculation here, I think, doesn't include, for example, I don't know, loops of these particles or something, right?
well, you could include it on the disk, So if you know
so here what is neglected are the non-trivial topologies. But you can have arbitrary loops in that blob that Henry had there in the blackboard.
Yeah.
So there are as many loops as you want, but this topology. So what's not included are e to the minus s naught corrections.
Well, I thought, so you say this includes, well, I guess I would have thought two things. One is if the matter fields were interacting, I would have guessed that this vertex has some factor associated to it, which you didn't include, right? But then even if the matter fields are free, I guess shouldn't there be virtual loops of?
I think the statement is this. So when I discussed this computation, we just did it in the probe approximation. But if you could, let's take a strongly coupled field theory with the right amount of supersymmetry, put it in ADS, and you tell me on rigid ADS what the boundary correlators are with no gravity whatsoever. I can then plug in your complicated formula for that correlator of some strongly coupled field theory into our formulas, and we still get some answer. I mean, by solve it, we mean reduce it to a finite dimensional integral. That's what we mean. We don't mean that, of course, you can't solve the strongly coupled field theory, but if you could, we could then just dress it up with gravity and tell you what to do.
Yeah. All right, why don't we thank Henry and Juan again?